Okay, a very good morning to all of my beloved students. So let's continue our lessons from where we stopped previously. So previously we stopped at question number 4. So we are going to continue from there. Okay. Okay, let's have a look together at the questions. Okay, M is an element from the period 4 of the periodic table. Stable oxide of M are MO and M203 and M304. An equal solution of M3 plus is yellow. Now, this is a very important keyword that can tell you what M probably is. And M can conduct electricity in solid and also molten states. What is X? So if you have to remember some of the colors of the ions that is possible for you to remember, and the one that is yellow in here is actually iron. M is about iron. Okay. Okay, so explain the conductivity of X. Supposed to be M lah. I accidentally put as X. Explain the electrical conductivity of X. So the question already says that M is a conductor. Okay, the question already says that M is a conductor. Of course, you don't have to say that M is can conduct electricity lah. Okay, so you have to explain from the angle of how does X conduct electricity. So X conduct electricity through delocalized electron. Okay. Okay, so that is for number 2. And then for number 3, compare the electrical conductivity of X with that of potassium and explain your answer. So X has a greater electrical conductivity compared to potassium, definitely. Why? Because X has a more delocalized electron from 3d and 4s orbitals. Because X has more valence electrons. Okay, so that is the key 2 keywords. So maybe you want to explain such as like this. You say that X has more valence electrons, hence can delocalize more electron than potassium. Okay. Okay, so that will be how we are going to explain why X can conduct electricity and how to compare the conductivity with that of potassium. B, explain the observation when aqueous solution of silver nitrate is added to tetraamine dichlorocobalt-3 chloride. Okay, so in here you need to understand how does the structure of tetraamine dichlorocobalt-3 chloride looks like. So this is the structure where you have a cobalt, tetraamine, then you have 3NH3. Okay, so this is how the structure probably looks like, and then dichloro, so you have 2Cl. And then you have, because it's cobalt-3 chloride, so you have 1 more Cl negative. This will be plus, okay? Okay, so in here, you have 1 chloride ion that acts as a free ion. So what happens if you dissolve inside the silver nitrate? So you're expected to form a white precipitate due to the presence of the free chloride ion. So this is the equation, as usual, explanation, observation, equation. So those are the 3 important key to answer such questions for inorganic chemistry. Okay, so I already highlighted for quite some time already. So I hope that you all will still be able to remember the 3 important keywords whenever you're trying to explain such questions. Okay, so this is for number 4. Okay. Okay, so without hesitation, let's move on to question number 5. Explain what is meant by the terms transition element. So as usual, there's 2 keywords that you need to remember on how to define the terms transition element. So transition elements that are elements that can form at least more 2 or more stable ions. At least 2 or more, not 2 or more stable ion with partial field d orbital. 2 or more stable ions with 2 or more stable ions with partial field d orbital, okay, or with incomplete field d orbital. It's better to use the word incomplete. Okay, field d orbitals. Okay, then number 2, explain how does the atomic radii on the transition element vary from chromium to copper. So the atomic radius does not vary much. Okay, why? Because both nuclear charge and screening effect increase gradually. Okay, due to the effective shielding inside the inner 3D orbital. So the inner 3D orbitals filled with electrons will increase the screening effect. So as the increase with the nuclear charge and screening effect, they cancel off each other. So as a result, the effective nuclear charge remain almost constant. So that is why the atomic radius does not vary much in this case. Okay. So that is the 3 keywords of how you are going to explain why is it that the atomic radius of the transition element does not vary much. B, sketch an energy level diagram to show the valence electronic configuration for chromium before and after electrons are filled. So before electrons are filled, 4s is lower than 3d, and after electrons are filled, 4s is higher than 3d, and you have to fill in such a way that the 4s and 3d all are single filled with single electrons. So definitely the next question going to ask you explain the variations or explain the irregularities inside here. So the two irregularities that you can see in here is in here 3D has a half set 3D orbital which has extra stability, and you can see in here that 4s is single filled with single electron, isn't it? So this is also considered as another anomalies inside our sections in here. Okay, so these are the two keywords. So 3D orbitals are half filled, which has extra stability. If you might want to add the words. Sorry. Okay, and then 4s orbital is single filled. Okay. Okay, so these are the things of how you comment about the filling of the electronic configuration inside the chromiums in there. Okay, so that is all for question number 5. Immediately we move to question number 6. What do you understand by the terms ligand? State the type of bonding that occur between a ligand and the transition element. So ligand is defined as the molecule ion or molecular ions that have a lone pair electron and are able to form coordinative or dative bond to the center metal ion. Okay, so you use a dative bond inside there. Okay, so the keyword in here is have lone pair electron and can donate lone pair to form coordinative bonds in here. Okay. Okay, then B, the following table lists some stability constant for the following reaction. So MH2O A plus Bl minus give MH2O6 minus Bl. So in here, they are trying to tell you that this is an octahedral structure from the questions in here. As you can see, you start with H2O6, so this is octahedral. So how many ligands substituting here will be how many water substitute out, and then ligand in here carries a negative charge in here. So for every single negative charge, we will minus off the charge inside the cations in here. Okay, so hope that you notice this. Okay. Where n is a whole number, rewrite the above equation in the case of experiment 1 and write the equation expression for the equilibrium stability constant and state its units. Okay, so in here you have to write the equations in here where you have FeH2O6 plus our ligand in here is SCN minus. Okay, so you substitute only one. You substitute only one, as the question already said. Okay, so you form FeH2O5 SCN2 plus H2O. So this is 1 mark. And then K stability is FeH2O6 H2O5 SCN2 plus. Typing error, sorry for that. Give FeH2O6 plus SCN. So the unit in here is the mole per decimeter cube. Mole per decimeter cube, because you only substituted one concentration only. Sorry, mole minus 1 dm cube. Mole minus 1 dm cube. Okay, mole minus 1 dm cube. Okay, so that is of how you are going to rewrite the stability constants for this one. Okay, so let's continue to the next question. So using the tables, data in the table to explain what would be predominant complex form when a solution containing equal concentration of both SCN and CN was added to the solution containing Fe3+. So in here, of course, CN minus will be more stable than the FeH2O5 SCN2+. How do you tell that? Because of the stability constant in the FeCN6 minus is greater. So that is why it is more stable. Okay. And then number 2, a solution containing equal concentration of Fe3+ and CO3+ was added to the solution containing CN3+. So from the stability constant, you can see that COCN6 minus is more stable than FeCN6, as the stability constant of the COCN6 3- is higher in here. Okay, so that is how we are going to tell which one is more stable in this case. Okay, okay. So with that, that is how we are going to answer for questions number 6 in here. Okay. Okay, so then let's go to number 7. Okay, so this is a little bit difficult because this is from very old past year questions. But never mind, we'll try to solve it together. Where Fe first react with A to form Fe2 plus. So here very obviously is oxidizing agent, okay, because you oxidize Fe to Fe2 plus. So you use any oxidizing agent. And then from B to Fe2 plus to become Fe3 plus is another oxidizing agent again. Okay, and when you add in Fe2 and then in Fe2 plus, when you added with excess cyanide ion, you form a complex in here. So what is a complex when we add with Fe2 plus? And then when we add with D, it gives a dark blue colors in here. Okay, and then for Fe3 plus, when you react with C, it gives a deep red solution. Okay, so if you do not have any idea of what is this question is all about, so you must pay attention to what about I'm about to explain, because in here it involves some of the things that you might already learn. It's just that you didn't realize. For example, as I already mentioned, A and B you must use oxidizing agents. So any oxidizing agent such as KMnO4, K2Cl2O7, or chlorine, or etc. in here. Okay. Now as for the C in here, when Fe3 plus dissolve inside the deep red solution, okay, so this is something that you have to memorize because in here, you actually form FeH2O5 SCN in here, 2 plus. Okay, so you have to memorize this on your own, okay, because that is what happens when you added this KSCN, you form a deep red solution. Okay, so this deep red solution is trying to tell you the formation of this complex. Okay, okay. As for D, what gives you a dark Prussian blue color? If you still remember in your SPM level last time, one of the way to test iron 2 and iron 3 is by reacting with this complex FeCN6 4 minus hexacyanoferrate 2 ions. Remember that? Okay. So hexacyanoferrate 2 ions, if you react with Fe2 plus, then you give a light blue. And then when you react with Fe3 plus, you will give a dark blue. And in here, this is the Fe3 plus that we are talking about that give a dark blue solution in here. Okay. So this is how you are going to solve for 7A in here. Okay, it can be quite challenging. Okay, so that is for question number 7A. So immediately let's have a look at 7B. Okay, identify gas Z in here. Gas Z in here is actually results of the hydrolysis of the FeH2O6 3+. FeH2O6 3+ have a very resemble properties to that of aluminium when dissolved inside water. So what happened when aluminium ion dissolve inside water? It can undergo what process? We say this. It can undergo hydrolysis. So iron can also do the same thing. So you form FeH2O5 OH minus 2 plus, okay, plus H3O plus. So it is the H3O plus in here that react with the magnesium to form the gas of hydrogen. So gas Z in here is hydrogen. So if you don't know, then never mind, it's just 1 mark. Okay. But now when you do this question, you should probably guess that it is due to the release of the hydrogen gas in here. Okay. Okay, number 3, name complex X and Y. So X is, as I already explained just now, hexacyanoferrate 2 ion, and then Y is the penta-aqua-thiocyanato iron 3 ion. Okay, so you must know on how to name them. And last but not least, draw the restructure for the ion X in here is FeCN6. And the dative bond must be formed from carbon, cannot be formed from the nitrogen. If you label from the nitrogen, then you're wrong. Okay. Okay, so with that, that is the challenging questions, which is number 7, or structure questions. Okay, so hopefully you'll be able to understand better. So with that next session, let's move on to the final structure question, which is structure question number 8. Okay, number 8 sounds like this. In the presence of methylamine, CdH2O6 2 plus reacts with to form a mixture of two isomeric octahedral structure complexes. So you have CdH2O62 plus 4CH3NH2 gives CdCH3NH2 4 H2O2 2 plus 4H2O delta H is negative 57. So the exothermic reaction is actually trying to tell you that equilibrium favor to the right side of the equations in here. Okay, so that means the complex form is stable. Okay, so methylamine is a monodentate ligand. Number one, state what is meant by the terms monodentate in this context. So monodentate are molecule or ion that can form a dative bond to the center metal ion. Okay, so or you have one ligand donor atoms to the center metal ions. Okay. Okay, and then number two, sketch the three-dimensional diagram to show the structure of CdCH3NH2 4 H2O2 2 plus. So you have to draw the structure on how does this take place. I'm so sorry, I also typed error in here. It's supposed to be cadmium, not platinum. Cadmium. CD, this one. Okay, so that is how their complex looks like. And the dative bond must come from the nitrogen. If you come from the carbon, then it's wrong. Okay, and then the dative bond from the water comes from the oxygen. Okay, so we are quite specific in here. So that means if you do not know how to show the correct arrow, we will presume that you do not understand on how does the dative bond, what is the atoms that is responsible to form the dative bond in here. So in here you have to be extra careful. Okay. Okay, then we goes to B1. State what is mean by the term stability constant. So stability constant is the expression of concentration of complex ion over the concentration of the metal ion multiplied by the power number of the ligands surrounding it. So that is how we are going to define stability constants. Okay, teacher, can I use equation to represent? Can, no problem. You can use the equation to represent, where you can say that K stability is equals to concentration of the complex MLN power of X over the concentration of Mn plus multiplied by the ligand power of N in here. Okay, so it's up to you whether you want to explain in words or you explain in the equations also can, up to you. Okay, so that is for number B1. Then we goes to B2. Based on the equation, express the stability constant for the reaction above. So you have to express for the equation above there. So K stability is cadmium CH3NH2 4 H2O2 2 plus divided by CdH2O62 times CH3NH2 power of 4. Okay. And then number 3, explain the effect of towards stability constant when the mixture above occur at a higher temperature. So in here, because the forward reaction is exothermic, so equilibrium will shift to the stability constant decrease. Because stability constant will shift to the left. Okay, stability constant decrease. Okay, as temperature increase, since forward reaction is exothermic. My bad. Equilibrium will shift to the left. Okay, so that is how you are going to explain for the effect of the temperature towards the stability constant. And last but not least, EDTA is a polydentate ligand. So when a solution of EDTA is added to the CdH2O62 plus, a new complex of CdEDTA2 minus is formed. So the value of the stability constant for the two complexes are shown below. Predict and explain the stability constants when a solution of ethylene diamine is added to the solutions. Okay, so this is the given by polydentate ligand. Okay. And then now you have solution of ethylene diamine. So ethylene diamine is a bidentate. So when it is a bidentate, the value of the stability constant should be in between these two. Okay, so you are able to form any values in between 4 to 10 to the power of 6 to 4 to 10 to the power of 16. So since NH2, CH2, CH2, NH2 is a bidentate ligand that bonded to a more stable compared to methylamine in here. Okay. So this is how you are going to explain why is it that this stability constants for ethylene diamine is going to be greater than that of the CH3 NH2 for H2O2 plus. Okay, so I hope that you understand how we are solving the structure actions questions for the D block elements. So we are going to continue to our essay questions. Okay, are you ready? Okay, so with that annexation, let's move on to the essay question. So today we are going to solve 2 essay questions, and then the rest we are going to reserve for our next lesson. Okay, okay, so let's have a look at the essay question number 1. Define the terms ligand, coordination number, and coordination compound, 3 marks, and state what shapes are possible for transition metal complexes with 4 or 6 ligand bonded to the center metal ion. Okay, so ligand is the molecule ion or molecular ion that have a lone pair electron and are able to form coordinative bonds to the center metal ion. This definition, you have no choice but to memorize them. Okay, whereas coordination number is the number of the native bond that can be accepted by the center metal ion. And last but not least, coordination compound is consists of a central metal cation that is bonded to the molecule or anions called ligands. Okay, so that is how you are going to explain the difference between ligand, coordination number, and coordination compound. And then number 2, state what are the possible shapes that is formed from with coordination number 4 and 6, in short, 6. Okay, so for coordination number 4, so you can form 2 types of possible shape, which is a tetrahedral and square planar. And then for coordination number of 6, then you form an octahedral. Okay, so it's very, very direct questions. So hopefully you can answer it well. Okay, so that is for question number 1A. Okay, so immediately we move to 1B. Draw the display formula showing the possible shape and name the following complex ion. So you have 3 things. 1, draw display formula. 2, state the shape. And then 3, name the complex ions in here. Okay. So in here, I'm going to prepare a table that shows you all of the shape all together in here. So CuCl4 3- is a tetrahedral structure. So you have tetrachlorocuprate 1 ion. There's no space, sorry, because of the my notes, I accidentally put a space in between here. But this one has dash. This one has dashes, but this one don't have. Okay. Sorry, I correct right now. Sorry, pardon me for my mistakes. Show you back. Okay, so this is how you draw the structure of the CuCl4 3-. So tetrachlorocuprate 1. So you can calculate the oxidation state in here, CuCl4 3-. So you have a Cu plus 4Cl is equals to -3. So Cl is -1. Okay, therefore Cu is equals to +1. As for FeCl H2O 5Cl2, so it's Fe plus 3Cl plus 5H2O. So it's equals to 0. So therefore, Fe is equals to +3 also. And then for CO, CO NH2, this one, so CO plus 2En plus 2F plus NO3- is equals to 0. So CO is 0, F is -1, NO3 is also -1. So CO is equals to +3 also. Okay, okay, and then for this one, in between here you should not have space. In between here you should not have space, so it must be very close. Okay, okay, so this is how the whole structure and also the naming for the complexes form. Okay, and then this one you have to somehow put a little efforts in learn how to draw the bidentate ligands as shown to you in here. It doesn't matter how does the arrangement goes on. So as long as you are able to show that how does the octahedrals form from the octahedral shapes is formed from the ligand surrounding it. Okay, then you'll be able to draw the structure correctly. Okay, and then the name in here, So you still follow the 4 steps that we approached earlier. So if you are still not sure, you can always check back to the YouTube video that I've already shows you on how to name the complexes. Okay. Okay. So with that, that is how you are going to solve for question number 1. Okay. So hopefully no problem. Huh? Okay. So that is for number 1. So with that annexation, let's move on to question number 2. By using different reagent, aqueous manganate can be reduced to lower oxidation state. So using data booklet to suggest reagent and write overall equation that can be used for manganese 4 oxide and manganese 2 ion. So you use any inert values lower than that of the positive 1.67 so that you can oxidize MnO2. You can reduce MnO4 minus to MnO2. So the most important 3 keywords in here is write the oxidation and reduction half equation, write overall equation, and calculate the inert cells in here. Okay, so for example, you can use let's say iron. Okay, so if you have MnO4 minus plus 8H plus 3 minus give MnO2 plus 4H2O and 2H2O. Sorry for that. Erase. Okay, and then this one is inert is equals to positive 1.67. And then you have any equations that you like, Fe2 plus, give Fe3 plus E minus. Okay, so any equations that is suitable. So at the end, you have MnO4 minus plus 4H plus 2 Fe3 plus. So inert cell in here is equals to positive 0.90. Okay, positive negative sign must be there. And then another one is for the half equations involving the MnO4 minus. So you can use any MnO4 minus that you like. Sorry, you can use any suitable reagent that you like as long as it's lower than positive 1.521. Okay. So if you, let's say you want to use chlorine, C2Cl minus, Cl2 plus 2 minus 1.36, for example. Okay, so your overall equation will be 2MnO4 plus 10Cl minus plus 16H plus 5Cl2 plus 2MnO2 plus H2O. So inert cell is equals to positive 0.64. Okay, so that is how you are going to deduce the overall equation, right? The inert cells in here. So these are the examples of the equations that you can propose. Of course, you can use any other equations that is appropriate to show on the how does the MnO4 minus is reduced to the respective ions in here. Okay, okay. So that is how you are going to do number 2A. Okay, then we are going to 2B. 0.0100 mole of sample oxo chloride ion of vanadium BOClX require 20 centimeter cube of 0.1 acidified potassium manganate for oxidation of the vanadium. By calculating how many moles of electrons was removed by MnO4 minus, the change in oxidation state of the vanadium is state, hence calculate the value of X in the formula of BOClX. Okay, so in here, you have to first calculate the mole of the KMnO4. So you use MV over 1000, so 0.100 times 20.0 divided by 1000, you get 0.2. And then since the ratio of the MnO4 minus to the VOClX is 2 to 1, okay, so you can see in here 0.01 mole. So 0.02 to 0.01 is 2 to 1. Therefore, the mole of electron removed by MnO4 is 2. It is cross, it is a cross reactions in here. So in another word, you remove 2 mole of the electron while vanadium accept 1 mole of electrons in here. Okay, so VOClX is equals to -1 plus 5. Oh, yeah, how do you know that the vanadium is +5? It's my fault because I didn't mention the oxochloride of vanadium 5. Okay, my fault. It's supposedly to be vanadium 5. I should have highlighted it, but never mind. VOClX is -1, so +5 plus -2 plus -1, x is equals to -1, so x is equals to 2. So therefore, the formula is VOCl2 here. Okay, I should have mentioned that vanadium 5. Okay, so it's my fault that the question is not complete. Okay, and last but not least, explain the observations when aqueous solutions of the silver nitrate is added to the number 1 triamine trichlorocobalt 3, and then number 2 triamine tetraamine dichlorocobalt 3 ion. So I hope that you can imagine on how does the structure looks like. So triamine trichlorocobalt, you have 3NH3. Then 2 chlorine here. Okay, this is the triamine trichlorocobalt. And then you also have for tetraamine dichlorocobalt. So you have NH3. Okay, and then this must be a plus, okay, because it's cobalt 3, so you have 2 Cl minus, so 1 Cl minus outside. Okay, so from here, when you add it to silver nitrate, you would expect that there is no precipitate is observed for triamine trichlorocobalt. Why no precipitate form? Because you do not. Because the Cl minus in here present as a ligand, so you do not form the white precipitate of the AgCl. But in the tetraamine trichlorocobalt, you form a white precipitate. Is observed due to there is a free Cl minus ion that acts as a free moving ion, so you form the equation Ag plus Cl minus give AgCl in here. Okay. Okay, so that will be all for how you are going to answer the essay for D block elements. I admit that it's a little bit challenging for answering the essay for D block element. That is why a lot of students, when they see D block elements in essay, they will try to not to answer it because it's not easy to answer. In some extent, yes, it's not easy to answer because you have to really understand on how is the properties of the transitions elements looks like. Okay. Okay, so I guess that is all for our lessons for today. So if you have any questions, you can always comment on the comment below, and then I'll try my best to answer as much as I can. Okay. Okay. So with that, that is all for our lesson today. So I'll see you all in our next video lessons. Okay. Thank you.